Okay, can everyone hear me out there?
Yes.
Okay, thanks. All right, so welcome to the last class of the semester. I mean, it's kind of hard to believe that the semester has kind of gone by. I know it's been an interesting experience probably for all of us, sort of dealing with the pandemic. And I just want to first thank you for, your patience. And there were some hiccups during the class, but fortunately we were able to actually, make it through. And so I've actually posted everything online so far. So all the class notes are online, and also all the lectures are available on YouTube also. So after this class, I'll actually post the notes and the lecture too. So there should be a complete set of notes and lectures to study from for the final exam. So as you know, the final is on Friday. I encourage you to get to the final early. So I'm going to try to get in at around 11:30. So that way I can start checking IDs and making sure everybody is there for the final exam. And it, I don't know if many people have experienced taking exams online, but I'm hoping that the exam will sort of at least be similar to the ones that you actually take in person. Okay, as much as possible. All right. Are there any questions at this point? No? Okay. All right. So the plan for today is there are some loose ends that I'd like to tie up. So a few topics that might be covered on the final that I should actually mention some things about. And then after I cover these loose ends, I'll leave it open for questions about the material or um, any of the stuff that we've talked about over the last couple of days. Okay. All right. So the first topic I want to discuss is the idea of linear transformations. Okay. So I'm not going to really emphasize everything I talked about in terms of functions, but you should be able to work with linear transformations because these are the relevant types of maps that we actually use in the class. So let me first remind you of the definition of a linear transformation. So a linear transformation is a function t from Rn to Rm such that two things hold. So one, if I take t on v1, v2, that's t on v1 plus t on v2, where v1 and v2 are in Rn. Okay. And two, t of lambda v is equal to lambda tv. So here lambda is a scalar and v is in Rn also. So the idea is that we're looking at functions which preserve the vector addition and also the scalar multiplication. And here's a consequence, and you could actually put this in as a property if you want. If I take the zero vector, it's always going to go to the zero vector too. Okay, actually it follows from 1 and 2, but we sometimes just put it in just to make sure we know that it has to take the zero vector to the zero vector. All right. So here's a classic example of a linear transformation. So suppose you have A being an m by n matrix. And so what you can do is you could let T of V be equal to A times X. So you just multiply a n tuple on the right by A and just matrix multiply. And this gives you a linear transformation. Now, on the other hand, if I fix a basis, like if I fix the standard basis for Rn, then I can actually write T as a matrix. So here's the other example. So let E1, E2 up to En be the standard basis for Rn. Okay. Then if I write T of X, and of course, T here is a linear transformation from Rn to Rm, then I can actually write this as the following. It's just T on the vector E1, and then I put it down the column. T on E2, and I put this down the column, and T of En, and I put that down the column, times X. So actually I can write it in terms of A times X, where A is this matrix over here. So I can represent T as A times X by just doing this. Okay, any questions on this? Now, we did a lot in terms of change of bases, so there's a more general form of this, but I wouldn't worry about it too much because it won't be an emphasis on the final. But let me just mention one thing. So here's a more general case. So suppose beta is a basis for Rn. Okay. And T is a linear transformation now from Rn to Rn. Okay. So I can actually represent T relative to this basis. And what you do is you write the coordinate T of X, T of V1 with respect to beta, and you put it down the column, T of V2 with respect to beta, and you write it down the column, and T of Vn of beta, and you write it down the column. So remember what it means when I take a vector y and I write it in terms of the coordinate. So what I do is I write y in terms of the basis. So I write y in terms of the basis, v1 up to vn, as a linear combination of the basis elements. Because it's a basis, the c's are going to be unique, and the coordinate you just obtain by just picking off the coefficients. Okay, so this is called the coordinate of y with respect to b. Okay, so the way you can get the coordinate is just by using Gaussian elimination. We've done many examples of that. All right, now there's a specific example where we saw this happening. So this is a special case of this. So suppose that T of X is equal to A times X, where A is an n by n matrix. Okay. And suppose that A is diagonalizable. All right, so that means that A is equal to PD P inverse, right? And recall that the D is obtained by taking the eigenvalues. Okay, so the lambda 1 up to lambda n are just the eigenvalues down the diagonal. And then the P is obtained by looking at the eigenvectors. And then you just put them down the columns, all right? Now, when you do this, basically you're changing bases. So when you do this diagonalization process, you can think of this as being a change of basis. So the theorem is that when you take B to be equal to V1, V2 up to Vn, so this is the basis of eigenvectors. Then your linear transformation T with respect to this basis is just the matrix D. So if you change bases to be a basis of eigenvectors or diagonalizable matrix, then your T relative to that basis is just the diagonal matrix corresponding to the eigenvalues. Okay, any questions on this so far? All right, now let me just review a few things in terms of one-to-one and onto. Okay, so we did this sort of early on in the class. So the linear transformation, so again, let me write this out. So this is Rn to Rm. So T is one-to-one if and only if when I take T of x1 and it's equal to T of x2, this implies that x1 is equal to x2. Okay. Now, that's the general definition of one-to-one. But in practice, what we can do is we can test one-to-one by knowing about the homogeneous solutions for A. So this happens, so this symbol is the if and only if symbol, right? So if and only if AX equals 0 has only the trivial solution. So remember, T of X can be written in terms of A times X. Okay, so to test one-to-one, we just have to know that the homogeneous system only has the trivial solution. Okay, any questions? We've done this before. So T is onto if and only if for every B in Rm, there exists, let's say, an X in Rn such that Tx is equal to B. Okay, so this is the definition for the map to be onto. So the image of T is all of Rm. All right, now there's a matrix way to sort of show this or prove this. So this happens if and only if AX equals B has a solution. Oops. So it has a solution for every B in Rm. Okay, so we just have to know that you can always solve this for every B in RM, and then we know that T is onto. Okay, so that's a very concrete way of actually analyzing the problem because we can use Gaussian elimination in both cases. All right, let me ask, are there any questions on this? Okay. So the next thing I just want to sort of tie up, or I just want to go over the type of applications that I expect you to sort of know how to do on the final. So these are the applications. All right. So I mentioned some of these beforehand. So you should actually be able to solve linear model problems. Okay, so these are problems that involve least squares or maybe least squares fitting a data. Okay, so the next one are the ones with difference equations. So if I give you a difference equation, you should be able to solve the difference equation by using the method that I presented. I think it was in the first lecture of the review. So this is an old topic. So balancing chemical equations. Okay, so you definitely had this on your first midterm. So I would actually review the problem on the first midterm to just make sure you know how it works. Of course, you have the book too, so it's not like if you forget, you can just look back at the book too. So, so you do have resources for actually knowing how to do this. All right, but you know the point is that you have to sort of you should know generally how to do this, and then make sure you perform the calculations correctly. 4, there were sort of economic models. Okay, so that actually involved sort of balancing things out too. Yes? Oh, sorry, is there a question out there?
I had a question real quick.
No problem, Duncan.
Are difference equations like the predator-prey model?
Yes,
Okay, gotcha. Thank you.
exactly, like predator prey.
Thanks.
They're basically the equations of the form like u of k plus 1 is equal to a times u of k with some initial value condition.
Okay, thank you.
All right. And then these economic models and then networks too. So I think this was all covered in one of the lectures, or maybe over like the course of a lecture and a half. And so those are all online. So these are covered in the lectures, and the notes are all on ELC. Okay, so all the class notes are on ELC. All right. Great. Okay, so that's actually all I have in terms of class material for review. So what I'd like to do now is I'd like to open it up to general questions or questions on the material, or even, you know, format of the final or anything like that. Okay, so let me open the floor up now.
I've got a question about diagonalization,
Sure, go ahead.
or sorry, about LDU decomposition.
Okay,
So I understand how to get from A to L times U prime,
yes.
but I'm not sure how to turn U prime into a diagonal times U.
Oh, okay. Hold on for a second. Let's do an example.
Yeah.
Shall we? In fact, hold on, let me just, I think I got my notes from last time. I have that example, and we could just do that example. All right. So wait, hang on for a second. Okay, let's see. Okay. All right, so let me do example here on LDU decomposition. Okay, so here's the example I gave you from last time. So quickly, A is going to be equal to 111 over 144 and then 148. All right. And what I get is that A is equal to L times U prime. And the L looks like this. It's 111, 111. Okay, so the multipliers are -1. You can kind of see that from the picture up here, okay? And the U that you obtain is 134,111. Okay, that's a U prime. Okay. Now, as you mentioned, you want to transform U prime in terms of D times U. So the idea is you take the diagonal entries off and make those the D, and then you sort of divide out the entries as long as they're non-zero from the rows, okay? So this is going to be 111, 111. Okay, so this still is L. Your D is 1, 3, 4. Okay, so you pull the entries off. But in order to compensate for that, I have to divide each of the rows of U prime by the corresponding entries. So 1, it doesn't do anything, right? But 3, if I put a 1 here, I have to put a 1/3 over here. Does that make sense? And then this one has.
Yeah, this makes sense.
And this is a, sorry. Should have a 1/4 here. LDU.
Because you divide 4 by 4, so it's 1.
1. Okay, that's right. Yeah, not a 1/4. Sorry, I'm not. I was just out of a 3-hour meeting, so sorry about that. Okay. Very good. Thank you. Everything good?
Yeah, thank you.
Okay, great. All right. Other questions?
Yeah, I had a question about diagonalization.
Yeah.
So when we're trying to find P inverse,
Yeah.
for the scenario that it's a 3 by 3 matrix, do we just have to do Kramer's rule for that?
You could do it by cofactors, or you can do it by Gaussian elimination.
Okay.
Okay.
So like simplify it down to like a 2 by 2 matrix. Is that what you're saying?
Well, you could, yeah, you can use the cofactor method,
Okay.
find everything if you want, or you can use the Gaussian elimination method to find the inverse. I would, if you get a problem like this and I ask you to find D and then find the P, and I don't ask you to find the inverse, I wouldn't necessarily find the inverse.
Gotcha.
Okay, so just make sure you read the problem to see how much you really have to do.
Mhm.
Okay. Because I know the inverse actually takes some work to actually figure out. Okay, other questions?
I have a question about orthogonal projections.
Okay.
So I know, like, we use the formula, like if we're using y equals y hat plus z.
Mhm.
But sometimes we solve for z and sometimes not. So I'm wondering how to know what exactly we're looking for.
Well, the first thing is, let me just say it this way. So orthogonal projections. Well, so the idea is that if you have W up here, okay, then, and you have this Y, So the idea is you want to decompose it in terms of two components, this y hat and then the z. Okay, so I think the important thing is to sort of realize where these vectors live. Okay, so y is a vector and y hat is going to be equal to z, sorry, y hat plus z. And y hat is in W. And z is perpendicular to W. Okay, so that's always sort of the case. And so sometimes you want, a problem will say, well, write y as something in W and something orthogonal to W. If that's what you want, then you just, you write the decomposition using the projection formula and everything.
Mhm.
Okay. If it says something like, well, I want to actually find a vector z, which is orthogonal to W, then, you may want, and sort of is part of this decomposition, then, you still have to do the process, but then you just subtract off y from y hat to get the z.
Okay, so if it's asking for a vector that's orthogonal to W, that's when you would need to find
Yeah,
Z.
so,
Okay,
so,
that makes
so
sense.
make sure you know the properties, because if you know what properties these vectors have, then it will help you to know what to do.
Okay, thank you.
Okay, other questions?
Yeah, so would you mind going over another I guess regression problem for the linear models?
Another,
I believe like for the applications, the what's it called? The fitting the best line to the data.
I could, although I probably I would, let me see if I actually have one up, okay, that I can just indicate. It's all sort of, they're all the same, okay? They're not, there's nothing that different about any of these. Let me see if I can get my notes here. Okay, so let's see. I have to remember when we did this. Okay, so projections and least squares. Oh, here we go. Okay, so you can see that, right? So maybe we can just go over this again. All right. So here's the idea. The idea is that you have all these data points. Like I have them over here, T1, B1, T2, B2, TM, BN, all right? And so we're assuming that all these sort of points live on the line. Y or R equals C plus DT up here, okay? So that gives you, because we're assuming that gives you a system of equations. Okay, and you can write your system out like I did right here, where you have one T1, one T2, one TM, with the C and the D, and then with the B's. So you have AX equals B, and this is probably going to be inconsistent. But we know how to actually find the best fit for this inconsistent system. And so what you do is you use least squares.
Gotcha.
Okay.
When do we include the residual column or residual vector in the equation?
What do you mean residual vector? You mean,
Maybe I'm thinking of the wrong name. It's it's somewhere in the book. There was like a different version of.
well, anyway, let's not
Yeah.
worry about it.
Okay.
I actually, if I'm not, I actually make the test. So, I wouldn't worry about it. I won't put something on that I haven't really talked about.
Gotcha.
Okay. But let me just, the point is that you have this system of equations and it's probably inconsistent. But, if you look at A, it, most likely has linearly independent columns. So you're going to probably have a unique solution for the least square solution. Okay, so you use the data, you get, sort of system of equations like this, and then you supply least squares. So we know least square solution has to satisfy A transpose AX is equal to A transpose B. We know probably A transpose A is invertible, and it's only going to be a 2x2 matrix. And I've described the 2x2 matrix down here, right? And then I computed out A transpose B too. So then you have your executive summary. You don't have to remember the formula. You just have to kind of remember how this kind of goes, okay? So here's the equation that the least square solution has to satisfy. It's just a 2x2 system of equations. You just plug it in and then you just solve.
Yep, makes sense. Thank
Okay.
you. Mhm.
Like I said, it's open notes, so it's not like I expect you to remember all this stuff. I mean, you can actually, you should have an overview of how things work. In case you need to know some details, you can kind of look them up quickly. Don't just rely on the book, obviously, but just kind of remember. And then if you'll have the formulas right in front of you if you need them. Okay. All right, other questions?
What was the condition that A transpose A formed an identity matrix?
The point was it wasn't the identity matrix. The point is that it's invertible in this situation. And the condition was that A has linearly independent columns.
Okay, so linear independence.
Right. So, I mean, just look at this example here. It's not the identity matrix necessarily, but, as long as A has linearly independent columns, A transpose A is going to be invertible. And if it's invertible, then the system down here will have a unique solution. Because I could just apply A transpose A inverse to both sides. Okay.
Yes.
Good. Okay, other questions?
Could you just quickly walk back through one of the A equals QR factorization problems that you did?
Sure. If I can find it, it'll be better. So let me just go back. Okay, let's see here. This was, what day was this? This was 12/2. Okay, so let me see what that one was. Nope, that's not the one. Okay, let's see. Okay, so this is orthogonal decomposition. Here's Graham-Schmidt. Okay, it's probably a lecture after this. Okay, so that's 11:23. Okay, so this is probably it over here. All right, so we have the Graham-Schmidt orthogonalization process. Okay, and these are the formulas for the Graham-Schmidt. Okay. Now, in talking about the QR factorization, we start with an m by n matrix, and we're assuming it has linearly independent columns. Okay. So if that's true, then we could write A in terms of Q times R, and Q is Q is an m by m matrix. Gives me a chance to even correct it here. Okay. With orthogonal columns. Actually, it should be an n by n matrix with orthogonal columns. Yeah. And R is an upper triangular matrix that's invertible. So R is actually square. Okay. And it has positive entries along the diagonal. All right. So in practice, how do you actually get the QR decomposition? Well, the first thing you do is, because you have linearly independent columns, we know that the columns will be a basis for the column space of A. All right.
Mhm.
So then what you can do is you can apply Gram-Schmidt to the columns to straighten them out. Okay, so you apply Gram-Schmidt first. And that's what we did over here, is we apply Gram-Schmidt. But you also have to normalize too. So what you want is you want to apply Gram-Schmidt to the columns of A, and then you also want to divide by the length. So this part here, let me write it in a different.
So is this A right here, are these like the Gram-Schmidt's already been applied to the columns and that was the result? Or is that
Oh,
the
no,
original
no.
matrix?
This is the original matrix up here.
Okay.
All right. So let's just go over the.
Oh, okay. And use the same one from our previous problem, then you got.
Yes, yes. yes.
Okay. Okay.
So let me write this out a little bit more carefully. I'll write it in like kind of a cooler color. I'll write it in green. Okay. So the columns here are obtained by using Gram-Schmidt on the columns of A. And normalizing. Okay, so we take the columns of A, we apply Gram-Schmidt, and then we normalize to get Q.
Okay.
Okay. So this is an orthogonal matrix. All right. And then what we do is we know that Q transpose Q is the identity.
Mhm.
And so we could just apply Q transpose Q to both sides, and that's how we can get R.
Okay.
Okay, and that's what we do.
Okay. That makes sense. Thank you.
Okay, so hopefully that clears up the issues. Okay, good. Okay. Other questions?
Yeah, I'm still confused why there's a 1 over square root of 20 in front of, like, does that happen all the time, or is it just problem specific for this?
All right, why is there a 1 over the square root of 20? It's because we normalize the lengths, and each of them have, it turns out that each of them has length square root of 20. See, otherwise we'd have to divide each column by the length. But it just turns out we get lucky here because each of them has length square root of 20,
Okay.
right? So this turns out to be, a very special problem in many ways. Otherwise, the first column could have like length square root of 10, and then you'd have to divide the first column by the square root of 10. The second column could have like the square root of 50. We'd have to divide that by the square root of 50. So then it becomes much more messy to kind of compute with. Does that make sense? I mean, you could see it from here, right? I mean, look at the vectors. You take 3 squared plus 1 squared plus minus 1 squared plus 3 squared. That's going to be 20. And then you just take the square root to get the length. And then you do that for every single column, and you can still get the square root of 20.
Okay. Do you do this for every A equals QR factorization problem?
Yeah, so you need to divide by the length, for every vector you get from Gram-Schmidt.
Okay.
Okay, good. Okay, other questions? Hmm. Yeah, one thing I would do is I would make sure I mean, you'll have your midterms in front of you too, potentially. So, I would still kind of briefly go over the midterm problems. Make sure you understand, how the midterm problems work. I think there's only 10 of them total, so. Because, problems like that could, appear on the final again. Ooh, what happened here? Oh, there it goes. Okay, other questions?
I have a question about permutation matrix or matrices.
Okay,
So when we do the LDU decomposition and we do a row exchange, we have to multiply the LDU by a permutation matrix.
that's correct.
So we just put that matrix in front of the LDU.
Yeah, so that's you actually, if you know what row exchange you have to do it first, you put it in front of A. So that PA is actually equal to LDU. Does that make sense? So
Okay,
you kind of have to know what row exchange you have to do first to A so that you can actually perform Gaussian elimination.
Okay, so to make it equal to A, you actually have to find the inverse of the permutation matrix
Correct.
and multiply it.
That's correct.
Okay, that makes
But
sense.
I would think of it this way. It's more of a, you take P times A and then you could write it as LDU. So the point is that if you take a matrix A up to multiplying on the left by a permutation matrix, then you could always write things in terms of LDU. Does that
Okay,
make
yeah,
sense?
that makes sense.
Okay, good. Okay, other questions? Oops. Hmm. Okay, so if there are no other questions, again, if you do have a question, just feel free to email me. I'll try to get back to you as soon as I can, about a problem. So if you're reviewing and, you need to send me an email, feel free to send me an email beforehand. Okay. I'm hoping that the final will be, I don't know, somewhat kind of, I mean, the other midterms are somewhat straightforward, and I'm hoping that, we've covered, basically everything in terms of, the knowledge you need to actually do the final. Plus you have your book now too, so that'll definitely help. So just make sure that when you're doing your final, you check your work, make sure you compute things carefully. I know a lot of times people lose points just because of, computational errors. Okay, and make sure you show all work because that gains you more credit too. Okay, great. So I will look forward to seeing everyone on Friday then. Okay. All right, so see you then.
Thank you.
Okay.
Thank you.
Thank you.
Thanks.